Addition reaction can be electrophilic, nucleophilic, or radical in character, depending on the type of species that initiates the process. Addition to simple carbon-carbon double bonds is normally either electrophile or radical induced, that is, of bromine, or addition of H pair. With a simple alkenes trans to butene, the two bromine atoms add on from opposite sides of the planar alkene, that is, anti-addition. These observations are explainable by a pathway in which one end of a bromine molecule becomes positively polarized through electron repulsion by the pi electrons of the alkene, thereby forming a pi complex. This spin then breaks down to form a cyclic bromonium ion, an alternative canonical form of the carbocation. Addition is completed through nucleophilic attack by the residual pair minus on either of the original double bond carbon atoms from the side opposite to the large bromonium ion to yield the mesodibromide. The addition reaction of an asymmetrical alkene is governed by Markovnikoff's rule, which states that the positive addendum will be added to that double bonded carbon which is less substituted, that is, greater number of hydrogen atoms are present. But however, in some cases we cannot apply the Markovnikov rule, but we can explain that the product by determining the stability of the carbocation through the reaction proceeds. We know that 3-degree carbocation is more stable than 2-degree, and which is more stable than 1-degree carbocation. So in case of an addition reaction of an asymmetric alkene, that alkene will proceed to production of that carbocation which is more stable. However, the addition of diborane to an alkene follows anti-Markovnikov rule, where the diborane is generated and probably complexes as the monomeric BH3 or borane with the ethereal solvent used for the reaction. BH3 is a Lewis acid and adds to the least substituted carbon atom of the alkene. Overall addition is completed by hydride transfer to the adjacent positively polarized carbon atom. There are a number of reagents that overall add 2 Wedge groups to alkanes. Thus, osmium tetroxide OSO4 adds to yield cyclic osmic esters, which can be made to undergo ready hydrolytic cleavage of their osmium oxygen bonds to yield the 1,2-diol. Cis-to-butene thus yields the meso-1,2-diol, that is, the overall hydroxylation is stereoselectively seen, as would be expected from osmium oxygen cleavage is a necessarily cis cyclic ester. Peroxyacids will also oxidize alkanes, that is, trans to butene, by adding an oxygen atom across the double bond to form an epoxide. Epoxides, though uncharged, have a formal resemblance to cyclic bromonium ion intermediates, but unlike them are stable and may readily be isolated. They do, however, undergo nucleophilic attack under either acid or base catalyzed conditions to yield the 1,2-diol. In either case, attack by the nucleophile on a carbon atom will be on the side opposite. Such attack on the epoch side will involve inversion of configuration. Thus, by suitable choice of reagent, the